Use case 1 is focused on distributed and dynamic critical infrastructure control and protection. Cyber-physical systems represent a solution for a continuous monitoring that must include adaptivity and automation features. Unfortunately, current approaches are static and system resources are wasted to respect performance constraints. FitOptiVis is about quality and resource management, runtime reconfiguration, resource and performance optimization. Use case 1 goal is to develop a monitoring system composed of smart cameras, drones and heterogeneous sensors. Leveraging on FitOptiVis approaches, the system implements runtime adaptivity and resource optimization. Use case 1 includes these components: smart cameras and network video recorders that acquire images and host video processing algorithms for intrusion detection, face recognition and movement detections. A multi-sensors gateway that collects data from sensors, aggregates processes and visualizes them and control actuators. Adaptive hardware accelerators with performance optimization capabilities. There is also a drone equipped with onboard camera. These components are integrated and installed at SAT water supply facility. Some details about the demo that will be shown. Tests have been conducted in a real operative scenario at SAT water supply. 2 different scenarios are considered. The goal is to show the adaptive behavior of video monitoring system integrating AI-based video content analysis to detect intruder and track his movements, face recognition to verify his identity, a drone acting as mobile camera, and the multi-sensor gateway. The monitoring system has different working points. Each time a camera detects an intruder, the system automatically switches to another working point corresponding to a different set of monitoring functions. In normal mode, the system monitors only the main entrance. When it detects an intruder, it switches to intermediate mode where intruder movements are tracked also inside the facility. If the system detects the intruder is moving towards water pumps, it finally switches to performance mode where also a drone is used as mobile cameras to patrol the water pumps area. Each working point corresponds to different requirements in terms of computational resources for video processing and bandwidth for transmission. We have collected and plotted GPU and CPU usage of a NVIDIA Tegra TX2 board used to elaborate the videos and the bandwidth required for transmission. Same numbers are reported also for a system with no adaptivity to highlight the amount of resource saved thanks to FitOptiVis. In this first scenario, an intruder is accessing the water supply facility through the main entrance. Camera 1 in green is recording and analyzing acquired images monitoring the main entrance, while camera 2 is only recording without applying any processing. When camera 1 detects the presence of an intruder, it generates an alarm and the system automatically enables video content analysis also on camera 2. When camera 2 detects the intruder is moving towards water pumps, it generates an alarm. Consequently, drone takeoff and camera 1 is oriented to monitor such area. Video content analysis is applied to detect the intruder also on the video flows acquired by the drone. When camera 1 detects the intruder is close to a water pump, it generates an alarm. The SCADA can automatically close this specific water pump. Per person it generates a warning and the system automatically enables video content analysis on camera 2 as well. When also camera 2 detects the person, another warning is generated and video content analysis is enabled on camera 3. When such camera detects the intruder is trying to enter the control room, it generates a further warning and the face recognition functionality is activated on camera 4 to verify the identity of the detected person. All FitOptiVis objectives are mapped in use case 1. In more detail, we have used QMRL to describe hardware accelerators and whole use case architecture. A draft model is reported in D6.2. Hardware accelerators have been developed using design time tools listed here. As demonstrated in this video and in other ones, we have implemented runtime additivity at hardware accelerator and at system levels. UC1 includes 6 components of FitOptiVis components library. Some of them are demonstrated in this video and in other ones. SAT owns the water supply and can be considered an end user. Having them on the consortium assures an effective impact and exploitation opportunities.